All right, we're recording now. All right, so again, welcome. Thank you all for coming. For those of you guys who don't know me or if it's your first time, my name is Juliet Verston. I work at the National Center for Ecological Analysis and Synthesis, or NCES, and I'm a data analyst, and I co-organize the Santa Barbara Our-Ladies chapter with Sam Sick, who is also working at NCES as a Arctic Data Fellow, and Ann Bowie, who is a PhD student at UCSB, co-advised by Holly Muller and Adrian Steyer. And with us today, we have Danielle, who also works at NCES and MLab, and also does data analyst work. And she will be talking to us today about parallel processing using R. I'm super stoked about. But a little bit of housekeeping first. We have another event coming up in June on June 22nd. This is going to be a Tuesday, not a Wednesday, how we normally do it, because we're going to be doing a Tidy Tuesday meetup, which will be a joint meetup with our chapter and also the Our Ladies Vancouver, which is really exciting. We have with us Jasmine, who is part of both right now, so she helped coordinate getting that together, and it'll be really fun. We're going to try to organize it in a way that every level of coding will feel comfortable joining and participating, so stay tuned for that event. And then, as always, our code of conduct, we cover this a little bit every meeting, but we expect everybody that participates and comes to our meetings to agree to this code of conduct. Our Ladies is dedicated to providing a harassment-free experience for everyone. We do not tolerate harassment of participants in any form. And this ensures that our environment of meetups stays safe and friendly. And if you would like to read the whole version of it, you can go to the link right here. Or you can go to our GitHub, which is also where that is directing you to. And then, without further ado, I think, Danielle, you can start sharing now.
Cool. Okay. Make sure that's big. Cool. Can everyone see? I'm assuming everyone can see the slides. Okay, so hi everyone. Thanks for coming to this workshop. I'm Danielle, and today I'll be giving you a hopefully gentle, very gentle introduction to parallel processing in R. Juliet just gave me a quick, background, but just for those of you who don't know me, I am a project researcher at UC Santa Barbara, and I work at the National Center for Ecological Analysis and Synthesis, as well as the Environmental Market Solutions Lab. I use R for work almost every day, but parallel processing is something that I don't use a lot and is relatively new for me. And really the motivation for me leading this workshop was because I wanted to learn about this topic. It wasn't because I was already an expert. I kind of had an idea of what it was, but I hadn't taken the time to try and wrap my head around it conceptually or try and figure out how to do it in R. So today I'll be relaying what I've learned over the last several weeks to all of you, and hopefully you can learn something new too. So, oops. Okay, so I just gave a bit about me. I wanted to pause and do a quick Zoom poll. Actually, Julia, I think it'd be helpful if you did it since I'm sharing my screen. Hopefully we can still do it at the same time. But there's going to be 4 questions, I believe, that pop up. So if you wouldn't mind just filling those out, that'd be awesome.
I only got the first one. I don't know if that's...
Yeah, I only saw the first one as well.
I think they have to be launched like...
It'll be one at a time,
yeah.
Gotcha.
Looks like we have most people responded. Good mix of people, lots of people who have come to Our Ladies SB stuff before, some beginners, newbies, which is awesome. Benefit of the virtual format for sure. Okay, you can go to the next one. Cool.
Mhm.
Good mix of skills. This talk is definitely geared towards people who have used R before, but you definitely don't need to be an expert. And a lot of this talk will be kind of about general concepts of parallel processing. And so that should hopefully be accessible to everyone. You can go to the next one. I want to see the answers to this one.
Mhm. Since I launched them, I can't answer them.
What's your answer for this one, Juliet?
I sometimes parallelize my code. Do parallel is the only one I know.
Cool. So it looks like we, again, have a mix. A lot of, I feel like a lot of people were kind of where I was at when I was first interested in this, kind of knew vaguely what it was, but don't really use it, want to learn more. I guess I'm glad there's no like secret parallel processing experts in the audience, although maybe that would be helpful, but we're all in this together. So, and then the last poll is just about your operating system, just because the way that parallel processing is implemented will change depending on what you use. So I'll talk a little bit more about that later, but I just wanted to be aware of what people were using. All right, so we have all three groups represented. Cool. Thanks, guys. Okay. Okay, so before we dig in, I just have to, put my disclaimer out there that I'm not a computer scientist. I'm just a person who uses R that wanted to learn about parallel processing. So everything I'm about to show you, I pretty much learned from Google and from tutorials that other very smart people put together. So on that point, I just wanted to flag the resources that I use to put together this workshop. They're all linked here, so you can check them out later. And I've also linked some other resources about the packages that we're going to cover today, which contain way more information than I could include in these slides. So I would definitely recommend giving those a read if you want to learn more about those packages and their functions. So first, a quick overview of what we're going to talk about today. I'm going to start off by talking about what parallel processing even is. So just going over some very basic concepts so we can understand what is going on when we're running code in parallel. I'll then give some advice on when parallel processing can be useful. Oops, looks like my slides are frozen. There we go. So next, I'll talk about when not to use it, which is arguably even more important. I'll then go through some of the R packages for parallelization, and we're going to talk about these 4 that are listed. And then I'll talk about some caveats and things to keep in mind. And then lastly, we will move over to RStudio, and I'll walk through some sample code that kind of demonstrates how each of those packages work in practice. And maybe we can throw those links in the chat. I think they were sent out in other ways too, but I've included a link to these slides and then the GitHub repo that has the sample code. So you can follow along if you'd like when we get to that point. So let's jump in. What is parallel processing? So the most basic definition in words is that it's a method where a process is broken up into smaller parts that can be carried out simultaneously, so also known as in parallel. So to help us kind of understand what that means, it can be helpful to think about what parallel processing is doing differently from non-parallel processing. So traditionally, software is written for what's called serial processing. This is the default type of processing your computer does. When you open R and run code, this is what's happening. And so to illustrate what serial processing is, imagine, oh, it's a little laggy. Okay, imagine you have a complicated coding problem where we're running some sort of complex analysis or doing some data processing. We might write a script to solve that problem, and that script contains a series of instructions or tasks that tell R what to do. So maybe we load data, we wrangle, we filter, we conduct some analyses. Those tasks are carried out sequentially, one after another, and they're carried out on a single processor on a computer, which eventually calculates the solution or solves the problem. So in this scenario, only one instruction or task can be running at one time. They are run one by one through that processor, and we have to wait for task one to complete before task two can start. In contrast, running tasks in parallel allows us to use multiple computing resources simultaneously to solve that problem. So if we have that same complicated coding problem, let's say this time we're going to divide it up into 4 smaller but similar kind of sub problems. And each of those problems still has the same set of tasks to complete, just like before. But this time, we are going to run those tasks simultaneously on separate processors. So they're all going to chug along all the same time, solving these separate subproblems simultaneously. And bam, they will talk to each other and give us the solution for everything at the end. That's kind of how I was able to wrap my head around parallel processing in a nutshell. It is definitely simplified, but that's kind of what helped me sort of understand it. So as you might already know, the primary benefit of using parallel processing is to speed up the amount of time that is required to run your code. It's not actually that your computations run faster, it's just that it requires less of our time because we split those computations across all of the resources that our computers make available to us. And I just want to take a moment to define a couple key terms. There's definitely a lot of computer jargon out there, but because this is a gentle introduction, we're just going to introduce a couple of the most basic terms. The first is a core. A core is the part of our computer that performs computations. Nowadays, most computers have more than one core. If you've ever used or bought a laptop that was like dual core or quad core, that's referring to the number of cores that are available in the laptop. There's a really easy way to detect how many cores you have in your computer, which I will show you when we get to the coding part of this presentation. The next term, a process, is just a single running task or program like R. Each core can run one process at a time. And lastly, a cluster is a term you may have heard in the context of high performance computing clusters, where there's a bunch of really fast computers all networked together. But the word cluster can also refer to the collection of cores that are on our personal computers. And so that's what we'll be focusing on today, how we can leverage the cores in our own computers to run code in parallel. Oops. Okay, so let's talk about when to use parallel processing. A term that I came across a lot when I was researching this topic is embarrassingly parallel. If your analysis could easily be separated into many identical but separate tasks that don't rely on each other, then it's what some people call embarrassingly parallel, and it is a good candidate for parallel processing. So some examples include things like bootstrapping or Monte Carlo simulations that are based on repeated independent samples that don't rely on each other, or kind of in general computations where you might split a data set apart by group and then run the same analysis on each group, that would also be a good candidate for parallel processing. What would be less useful is if you had something like this function where each step relies on the step before it. So they cannot be completed at the same time. So in this simple example, B relies on the argument A, then C relies on B, and D relies on C, and then you finally return the last thing. And you couldn't split that apart because each of the steps depend on each other. So there's no way to run something like that in parallel. If you do have a task that's well suited to parallel processing, another important factor to consider is if it is computationally intensive and takes a lot of time to complete. I'll talk more about this later, but parallel processing comes with a lot of costs. So to get the most out of it, it really only makes sense to do on code that is non-trivial and really takes a long time to run. Moving on to when not to use parallel processing. There's actually a lot of reasons. Just because we can run everything at the same time doesn't mean we should do that. And what I quickly learned is that parallel processing is not magic. When we find ourselves in the situation, as most of us do, where our code is taking a super long time to run, it might seem intriguing or even fun to speed up our code by running it in parallel. But what we really should be doing is profiling our code to figure out why it is slow in the first place. So as a first step, always profile your code. And that basically means try and find the biggest bottleneck, see if you can eliminate it and repeat it until your code is fast enough for whatever you need it for. And this is actually a link to the profiling chapter in Hadley Wickham's Advanced R book, and I would definitely recommend giving it a read if you haven't already. A few of my own suggestions that may help you speed up your code include embracing R's strength in vectorization, trying to avoid things like using for loops that make objects grow in size. You could also try using functional programming, so the family of apply functions or map functions from the per package. They may be able to speed up your code for you without much effort. And finally, definitely try out different packages. I'm a huge tidyverse fan, but data table might be a better option for certain analyses that work on really big data just because it's so fast. Additionally, parallel processing might not be the right tool for the job. If this image, conjures up some very specific memories for you, your computer in that situation may have been memory limited, meaning that your computer didn't have enough RAM to store what you were trying to process. So if you've ever tried to open some really large data in R and R freezes and starts sounding like it's about to blast off into outer space and takes a while to shut down, that's a pretty good indication that you're having a memory problem. And so in those situations, you could try chunking your data, so splitting it up into parts and computing on it separately, or you could try simplifying your data. One case that comes to mind is with spatial vector data like polygons. If you have really high resolution, detailed polygons, like say a coastline, those can really slow down your code. And in a lot of cases, you don't need all of that detail, and you could just simplify that polygon and then be on your merry way. But if you're memory limited, splitting that across cores isn't really going to help you. So it's a good thing to keep in mind what your actual problem is with your slow code. Another reason that we may want not to use parallel processing is that it might not be efficient. A really important thing to keep in mind is that the process of actually splitting up your analysis and divvying it up across all those cores comes with computational overhead, meaning it takes time. So if your process is small or your code is already relatively fast, the overhead of parallel processing might actually slow down your code, and that we obviously don't want that. So that's again why parallel processing is really most effective for very computationally intensive, slow code that has the most to gain. So just because our computer has 8 cores doesn't mean that we can make our code go 8 times as fast, and that's because of the overhead involved. Similarly, the amount of speed that we can gain from running code in parallel is limited by the amount of code that can actually be parallelized. This is actually mathematically defined, and essentially what it shows is that the more of your code that can be run in parallel, the more gains you might have. But even if you have code that's great for parallelization and a computer with a ton of cores to work with, you don't have infinite gains in efficiency, of course. So I guess all this to say, if you're thinking about using parallel processing, it can be very useful to think about these things ahead of time so you have realistic expectations of how much you can actually benefit from setting that up. Just a few more caveats and things to keep in mind. I mentioned this before, but parallel processing is implemented differently depending on the operating system you have. I won't go into too much detail here, but there are 2 different ways: forking and sockets. Forking is generally faster, but it doesn't work on Windows, and it may cause problems in IDEs like RStudio. And on the other hand, sockets are a bit slower, but they work across operating systems and they're safe in IDEs. Different packages will use different methods, so it's important to know which one each package is using so that you can use the correct one for your operating system and set it up properly. And if you want to learn more about these methods, the resources I linked at the beginning of the talk have a ton of information on that. Second, debugging can be a little tricky. Again, it can differ from package to package, but you may need to explicitly build in error catching so that you know where errors are occurring across the different cores. And lastly, if you are using random numbers in your analyses, you'll need to be careful when generating those across the different processes. But R does have some guidance on how to deal with that. Okay, the last section of the talk before moving on to live coding is about the different R packages that exist for parallelization. Or making your code run in parallel in R, and I'm going to give a really high level overview here of the different packages we could use. There's kind of 2 main frameworks. The first is the parallel package, which is a base R package. It's been around for a long time, I think over 10 years, and it's the backend for a lot of parallel processing packages out there. More recently, the future package has come onto the scene. It's a bit newer, it's a bit more user-friendly, and it's probably the one I'd recommend trying out if you're able to choose between the 2. And like I said, there's a lot of packages out there that exist, but typically they use either future or parallel behind the scenes. So today we will cover 4 different packages: parallel, dupar, for, and future apply. But there are others, and I've linked some resources there. So starting out with the parallel package, and on each slide I have some code. You definitely don't need to digest it now because we're going to walk through it later, but I just wanted to include some skeleton code on each slide for reference. But so yeah, the parallel package provides parallel versions of the apply functions that are available in base R. So in this example, I'm just using lapply to calculate the square root of every element in this vector of numbers 1 through 10. It's a very simple example. And the parallel version would just be using this function mc_lapply. So it looks very similar to the lapply function. You just have to specify how many cores you want to use, and that's pretty much it. Something to note is that these MC apply functions will not work on Windows because of those operating system differences that I mentioned. These functions use forking, which isn't compatible. So if you have a Windows machine, you would use a different function that uses the sockets method. It takes a little bit more setup because you have to first tell it to make a local cluster on our computer via sockets, but then you pass that cluster to this par apply function, which will produce the same exact result as MC apply. Moving on to for each. For each is a way to more or less preserve for loops in parallel to an extent. So similar to our example before of using lapply, we could use a for loop to calculate the square root of our vector. And then to run in parallel, we would use this for each function. And we do have to do a little bit of setup with this kind of do parallel package or do future package. The for each package allows you to choose which backend you want to use, parallel or future, or there's others too. I just wrote these two for the purposes of the slide, but you basically tell it which backend you want to use and then write your for loop in this kind of interesting format, which uses this do par operator, which tells the computer we're parallel processing. The next package is fur, which is kind of my favorite because it provides functions that can more or less be swapped out perfectly for the map functions from per. So here we're calculating our square roots with the map double function. And to make that parallel, all we have to do is first tell R we want to parallel process using this plan function that I'll talk about when we code it later. And then the function names are the same, except they have the word future in front of them. So those are pretty straightforward and easy to remember. And then lastly, we have the future apply package, which gives parallel versions of the base apply functions, but using future this time instead of parallel. So similar to before, we just have to set up our parallel processing session with this plan function, and then we can convert lapply to a parallel version by swapping it with future lapply. And all of these, the future kind of ecosystem of packages, they have future versions of every apply and map function that you might use, which is really handy. Okay, so that's it for slides. We're ready to move on to the sample code, but before I do, I haven't been monitoring the chat, so I thought we could pause for questions if some have come up.
Yeah, Danielle, it looks like Svetlana asked what it is considered to be a small process. Do you have a sense of that?
That's a really great question. I don't know if I have the answer for that. I read one article that said if it takes more than a few minutes, maybe you should consider making it run in parallel, but I don't think one size fits all for those sorts of solutions. I think you would want to make sure that whatever you're trying to make faster will actually like have the gains, or will actually get the gains from like the efforts, and maybe you can like test that out on a smaller portion, but I don't know if there's like a like threshold for, you know, you should run it in parallel or you shouldn't. Not exactly sure. I mean, if something is, oh,
Go on. No, you go on.
I was just gonna say if something is like, I don't know, like taking days to run, you know, and it's just like chugging along, it seems like there could definitely be efficiency gains made. Then like, I don't know, something like that seems like it could benefit.
It looks like Sophia asks, when you run something in parallel, will you be able to use the computer to do these other things? You tried that.
Yes, so that's a great question. So there's some debate on the number of cores that you should use when running things in parallel. You can like reserve cores. So if you wanted to like run things in parallel and you wanted to also save some room for other processes, you can do that because you're telling the computer how many cores to use. I don't know. I think it depends. Like maybe if there's something that's, if you're running a process that's like very computationally heavy, maybe you want to have it run in a computer where all of the cores can be firing at once. And all of that energy is dedicated to running the code. But you don't have to do that. And some packages will default to like half the available cores or maybe n-1 or something like that. But yeah, the answer to your question is you can definitely do other things while you're running code in parallel. Anything else? I will stop sharing my slides and reshare our studio. Okay.
Wait, there's one more question, I think.
Oh, yeah.
Let's see. Can you parse XML files in parallel processing? Would this be a good application?
I think you can do anything in parallel. I mean, definitely, yeah. If you made a function where you had your like parsing code and then you had your list of files, 100%, that seems like a great application. So if your parsing code is taking a super long time to get through each file, then yeah, I think you could definitely speed it up that way. Okie dokie. So I am in, sorry, if you're trying to follow along and you've cloned or downloaded this repository, there's a folder called sample code where I have a blank version that I'm going to be coding in. There's also a version just called sample code that has all of the kind of answers already filled in if you'd just like to follow along with that one. I'm going to use this blank one. Let me move Zoom out of the way. Okay, so this file is just going to contain kind of sample code snippets from the packages that we just talked through. If you haven't already and you'd like to code along, you're going to need to install these packages, the for each, do parallel, for, and future apply packages. If you need to install them, you can just uncomment these lines and run them. And then I'm also going to use dplyr for a little bit of data wrangling and the package TikTok, which is a fun way to time how long code takes to run. So similarly, install those packages if you need them. And then I'm just going to load dplyr and TikTok into our with the library function. Cool. Okay, so we're going to start off with the parallel package. As I mentioned, it is a base R package, comes with your R installation, so you don't have to install it, you just have to load it. So we can do that with library. Cool. And one of the first things we can do with parallel is check how many cores your computer has kicking around. So we can use the function detect cores to do that. So if I run that, it's telling me that I've got 8 cores on my laptop, which is a MacBook Pro. So obviously that answer is going to be different depending on what computer you're running R on. If I was using the RStudio server that I get to use at work, there would be a lot more cores available for me to use. And yeah, this is just some text that kind of talks about what I mentioned before. You can decide how many cores you want to use for your purposes. And in this example, I think I'll use 7, so just like one less than the amount that I have available. Okay, so the simplest way to use the parallel package is using the series of apply functions, or the parallel versions of the apply functions. So as I mentioned, if you use any of those, like lapply, this will look familiar to you. We're going to kind of try out these packages in R by writing a very simple and hopefully easy to read, but purposefully slow function for our testing purposes. It's kind of a needless function, doesn't really do much, but I think it's a clear way to kind of show how to use these packages. And so I'm borrowing a function that Grant McDermott wrote, and I linked his resources, or the lecture notes that I used where that function is. But it's basically a function to calculate the square of a number and then just like waste some time. So we're going to call this function slow square. And our function is going to have one argument. So we'll first get the value of x squared. And then we're just going to make a simple tibble that has the results, including the value of x as well as x squared. And then we're going to tell R to take a nap for 2 seconds and then return that tibble. So obviously this isn't something that we would use in practice, but this is what we'll be doing testing on. So I'm just going to run that so we have our function in our environment. So we can now test out that slow function to see how long it takes using regular non-parallel processing. So I'm going to start out by using lapply, and I'm going to run that function on a few numbers and then bind the results into a tibble because lapply returns a list. And I'm going to time how long that takes using the tick and tock functions from the tick-tock package. So I'm going to start the timer. I'm going to add some text that will just print to the console. And then I'm going to say lapply. I'm going to give it a vector of 1 through 5. Apply our slow function. And then I'm going to use bind rows from dplyr. Yeah, I'm going to use the dplyr pipe and then bind rows from dplyr to bind it into a tibble. And then I will end the timer. So let's see how slow it is. Okay, so it took about 10 seconds, which makes sense because it's a very quick thing we asked it to do with a 2-second nap times 5. So that sounds about right. Let's see if we can speed that up using the MC lapply function from Parallel. So the first thing I'm going to do is just define the number of cores that we want to use. I'm just going to save it as an object so we can use it later. I'm going to generate the number of cores -1. I'm just going to run that. So we're telling R that we are going to use 7 cores here. I will initialize the timer. And then I'm going to use MC apply instead of apply. Still going to use the 1 through 5 vector. Basically, it's going to look really similar to lapply, except there's one additional, oops, square, square, square. We're going to use one additional argument that tells it how many cores to use. MC cores equals n cores, which is 7 in my case. And then I'm going to pipe that whole result into our bind rows function. And then I will end the timer. And let's see what happens. Okay, so that took 2 seconds. So that's a lot faster. Again, this is like such a simple and needless example that you probably wouldn't be doing something like this, but it did in fact run the code across those 7 cores and it brought it back to me in 2 seconds. So that's cool. If you have a Windows machine, the function you will need to use from Parallel is that parallelization function. There's a little bit more setup involved. First, you need to make a local cluster with this make psoc cluster function. So I'm going to define that as an object and say make psoc cluster, and I'm going to tell it the number of cores. And I believe that stands for parallel sockets. So we've made the cluster. We can then run the code. I'll first start a timer. The parallelization function will first call that cluster as its first argument, and then the rest will look familiar. Okay. Cool. And then I'm going to end the timer there. So if I run this, oh no, there's an error. Okay. I just wanted to demonstrate this because it was really helpful for me when I was stepping through this. With the parallelization function and with any socket-based parallel processing function, so the one you would have to use on Windows, they work across all operating systems, not just Windows. But yeah, so with sockets, you have to basically like copy any packages you need to the different parts of the cluster. So with forking, it kind of like transfers everything you need without effort. With sockets, you have to tell it this, I need this package and this package and this package on all of the cores. And so you have to kind of explicitly export that package that you need. And so this failed here because I am using the tibble package in my function here, and it didn't know what that was. So in order to fix that, we have to export tibble into our local cluster. So I'm just going to copy and paste this code into this new section. And right after I define the cluster, I'm going to run this function where I say on the cluster, we need to load tibble. And it should work now. There we go. So again, that took about 2 seconds. At this scale, the parallelization function was about as fast as the MC apply function. So moving on to for each, as I mentioned, for each kind of enables you to use loops rather than the apply format we used in the previous example. The code kind of has this general format where you have this do par operator that tells R the computation is going to be done in parallel. And there's a little bit more setup involved because we have to first register the parallel backend that we want to use. So I mentioned you could use the parallel package or future. And so we have to explicitly set that up before we can run our for each code. So let's get into this. I'm first going to load for each. And I'm also going to load do parallel. You could use do future or another, but in this example, I'm going to use the parallel package as the backend. And then I am going to tell R that we are registering our parallel backend with the number of cores that we have defined. And I believe in this function, if you leave it blank, it will default to half the number of cores available. Okay, so that is run. So now I can write my code. Let's set up a timer for each. Okay, so it's sort of like a for loop in that you have, you first state what you're going to be running your code over. And then you have the do par operator. So we're telling R it's going to run in parallel. And then we tell it what we're going to do. So I'm going to put our function in there, and it's going to be run over all elements of I. I have this note at the top here. There is a combine argument in for each that allows you to specify how to combine the results of the for each function, which by default will return a list. So what I want to do is get a tibble at the end. So I'm going to add the argument combine equals bind rows. So it will bind the output for me. And then I'm going to end the timer. Okay. Bam, so fast. So there we go, that worked. And then one thing to note is that for debugging, you can replace this do par operator with just do. So if I did that, that will then kind of revert the computation back to a serial method. And that can be helpful for trying to debug your code. So as you can see, that's still working. We went back to the slower time. Okay. Moving right along to Fur. As I've mentioned, it's part of that future ecosystem, a little bit newer than the parallel package. It's supportive across any operating system, and it's meant to be a bit more user-friendly. If you use any of the map or walk functions from Purr, the equivalents in Fur look very, very similar. So let's get set up here. I'm going to first load my Fur package. The next thing that you have to do is set up your parallel processing session. And the function from Fur that you use is called plan. It actually might be from future, I'm not sure which. It's called plan. And within plan, you basically define the method that you want to use to do your parallel processing. So there's a few different options. Some correspond to forking, some correspond to the sockets method. I would definitely recommend looking up the documentation for this function to read more about it. But I'm going to use one called multi-session because I know that will work across all operating systems for the purposes of this workshop. And I'm also going to tell it the number of cores I want with this workers argument. So again, I'm going to call it n cores. And I believe if that is left blank, the number of cores, it'll default to all available all available cores. Okay, so once you have that set up, we can run our code. So I'll start the timer. I'm going to use the future map data frame function, which is written just like map data frame, but with a future in front of it. I'm going to put our vector in, our function. And a fun thing you can do is add a progress bar, which is kind of silly for something that takes 2 seconds, but purposes of showing you, I'll turn it on. And then we'll end our timer. So let's run that. Okay, so there we go. I actually don't know why the fir package in this case, or the fir functions in this case, are a little bit slower than the other ones. If anyone out there has an idea why, I'd be super curious. I didn't quite figure it out, but it is obviously faster than the serial version. Okay, and then the last package is future apply. Again, it's part of that future ecosystem, and it's going to provide parallel versions of the base apply functions, but it's going to use future instead of parallel, which is what the MC apply functions did in that first example we went through. So it's going to look really similar to how you set up the fir package. First going to load it. I would set it up the same exact way as here. So I'm just going to copy and paste, but I don't need to run it because it should already be open, I think. And then I can write my code. So I'll start my timer. And it's just going to be a function called future apply. It's going to look exactly the same. And we'll bind the rows of the results. Okay, let's run that. And there you have it. So those are all my examples. Obviously, they're very simple, but hopefully they gave you an idea of how the code can be written around a function. Yeah, so if there's any questions, definitely happy to take them.
That was awesome, Danielle. I had no idea what any of this meant when I was first reading your meetup blurb, so this is incredibly interesting. It's fun to see like how much faster a very simple, like relatively fast task can get already. That was really, really cool.
Yeah, I think, yeah, it was definitely interesting to learn about. But one thing I did take away is that I probably don't need to use a lot of parallel processing in like what I'm doing right now. It's not the right tool for every job, but it is really good to know what it is and how to do it in the case that it is, you know, something you want to pursue.
I was going to ask you, do you have an example where you like a part of your project or work where you thought you might use this or have used it?
Yes. One example where it was totally necessary was I was using a package called Taxize that connects to different like taxonomy databases. And so you have to connect to these APIs and pull a bunch of information down, and it takes an incredibly long amount of time to pull down information for, you know, thousands of species or whatever it is you're interested in. And so in that case, I used Fir, or a colleague helped me use Fir to run that faster, and it went like, it would have just taken like many minutes to run, and it was sped up to be really quick. So yeah, I think it's about like identifying which problems could really benefit from parallel processing, and that could take a little bit of thought, but yeah, it's definitely a useful tool to have in the toolkit.
would you like recommend trying to, if you're going to try using parallel processing, trying it on a small scale, like a subset of whatever you want to accomplish before like letting it loose? Or is there any drawback to just trying it with everything at, first go? Or do you run into the problem of potentially crashing? I don't know, is that a problem that you could run into, like crashing your machine?
Yeah, I mean, I think I've definitely read that if you just really went for it on something of like an astronomical size, you could definitely give your computer too much to do. So it might be worth trying it on smaller problems first, but that's just my naive answer.
Yeah.
I have a question for about the for each. So like, it looks like you can kind of use it as a replacement for a regular for loop. But I'm wondering if you run into any like caveats or situations where that might not be the best. Like I'm thinking for some of my own work, I'm generating a lot of plots that are specific to locations and then printing them into a PDF. But we're talking, anywhere from like 300 to 500 sets of data analysis and then plot generation and those types of things. So I feel like this could be really helpful for speeding up code, but I'm wondering like, if things are printed in a certain order, or if there's anything like, I'm just trying to wonder like if the parallelization for like a for loop can have any implications at the end kind of result, especially if you're talking about data viz.
I'm not entirely sure. I mean, I've definitely used for loops in a similar way before to like generate plots, like looping over countries or species or something like that. So I think like if your code is optimized in that format, you might as well do for each to contain it in that format. And I think there's something also to be said for having to make the least changes to your code. I mean, it's obviously a balance. You don't want to like be so stubborn that your code is super inefficient and like it could be better, but like you don't want to edit it. But I think like if you have code that runs well, but it just takes a really long time and it's a for loop, might as well stick, with that format and see how much better it can get.
Cool.
Looks like we have a question in the chat that says, ask if you can explain the difference between multi-session and multi-core again, and why multi-core can't work with an IDE.
Yeah.
Yeah.
I will give this my best shot. So the difference between multi-session and multi-core, this is with the feature package, is like there's been a lot of developments in the last year around this, and there's been like some recent changes where which one you should use has changed in terms of like the package developers recommendations. So I would definitely like first recommend like reading more from the package resources that are available. But my understanding is that one uses forking and one uses the socket approach. And so forking is not supported on Windows. So in that case, you'd have to use multi-session, which uses sockets. I don't understand why multi-core has issues with IDEs. It's not all the time. I know some people like have been able to use them successfully, but if you look at the package documentation, like there's a note in there that basically recommends you use multi-session to avoid potential issues with running multi-core in an IDE. Yeah, it's a little fuzzy. I think it's like kind of in active development, but that's what I was able to gather from what I read. I don't know about plan remote. I'd have to read up on that. I think the birds are also excited about parallel.
Can you hear them still? Sorry.
Cool. Any other questions? Well, thanks all for coming.